2.7 Games with infinite strategy sets. Games where the strategy set of one or more players is infinite cannot be represented using a table or set of tables. However, all the concepts introduced in this chapter can still be applied. In this section, we will focus on the notion of Nash equilibrium. We start with an example. Example 2.2, there are two players. Each player has to write down a real number, not necessarily an integer, greater than or equal to 1. Thus, the strategy sets are capital S sub 1 equals capital S sub 2 equals open bracket 1 comma infinity close parentheses. Payoffs are as follows. Open parentheses pi sub 1 is the payoff of player 1, comma player pi sub 2 the payoff of player 2. X is the number written by player 1, and Y is the number written by player 2. Colon. Pi sub 1 of X comma Y equals a set with two outcomes. The first is X minus 1 if X is less than Y, and the other outcome 0 if X is greater than or equal to Y. And pi sub 2 of X comma Y equals the set Y minus 1 if X is greater than Y, and 0 if X is less than or equal to Y. What are the Nash equilibria at this game? There's only one Nash equilibrium, namely the ordered pair 1, 1 with payoffs 0, 0. First of all, we must show that the ordered pair 1, 1 is indeed a Nash equilibrium. If player 1 switched to some x greater than 1, then her payoff would remain 0. Colon pi sub 1 of x comma 1 equals 0 for all x an element of open bracket 1 comma infinity close parentheses, and the same is true for player 2 if he unilaterally switched to some y greater than 1. Colon pi sub 2 of 1 comma y equals 0 for all y an element of open bracket 1 comma infinity close parentheses. Now we can show that no other pair x comma y is a Nash equilibrium. Consider first an arbitrary pair x comma y with x equal to y greater than 1. Then pi sub 1 of x comma y equals 0. But if player 1 switched to an x hat strictly between 1 and x, open parentheses 1 is less than x hat, which is less than x, her payoff would be pi sub 1 of x hat comma y, close parentheses, equals x hat minus 1 is greater than 0. Recall that by hypothesis, x equals y. Now consider an arbitrary ordered pair x comma y with x is less than y. Then pi sub 1 of x comma y equals x minus 1. But if player 1 switched to an x hat strictly between x and y, open parentheses, x is less than x hat, which is less than y, her payoff would be pi sub 1 of x hat comma y equals x hat minus 1 is greater than x minus 1. The argument for ruling out pairs x, y with y less than x is similar. Note the interesting fact that for player 1, x equals 1 is a weakly dominated strategy. Indeed, it is weakly dominated by any other strategy. X equals 1 guarantees a payoff of 0 for player 1, while any x hat greater than 1 would yield a positive payoff to player 1 in some cases against any y greater than x hat, and 0 for the remaining cases. The same is true for player 2. Thus, in this game, there is a unique Nash equilibrium where the strategy of each player is weakly dominated. Note, the rest of this section makes use of calculus. The reader who is not familiar with calculus should skip this part. We conclude this section with an example based on the analysis of competition among firms proposed by Augustin Cournot in a book published in 1838. In fact, Cournot is one who invented what we now call Nash equilibrium, although his analysis was restricted to a small class of games. Consider n greater than or equal to 2 firms which produce an identical product. Let Q sub I be the quantity produced by firm I. Open parentheses, I equals 1 ellipsis n, close parentheses. For firm I, the cost of producing Q sub I units of output is C sub I, Q sub I, where C sub I is a positive constant. For simplicity, we will restrict attention to the case of 2 firms, open parentheses, n equals 2, close parentheses, and identical cost functions, colon, C sub 1 equals C sub 2 equals C. Let capital Q be the total industry output, that is capital Q equals Q sub 1 plus Q sub 2. The price at which each firm can sell each unit of output is given by the inverse demand function, capital P equals A minus B capital Q, where A and B are positive constants. Cournot assumed that each firm was only interested in its own profit and preferred higher profit to lower profit. That is, each firm is selfish and greedy. The profit function of firm 1 is given by pi sub 1 of Q sub 1 comma Q sub 2 equals capital P Q sub 1 minus C Q sub 1 equals open bracket A minus B of Q sub 1 plus Q sub 2 close bracket. Q sub 1 minus C Q sub 1 equals open parentheses A minus C close parentheses Q sub 1 minus B of Q1 squared minus B Q sub 1 Q sub 2. Similarly, the profit function of firm 2 is given by pi sub 2 of Q sub 1 comma Q sub 2 equals open parentheses A minus C close parentheses Q sub 2 minus B of Q sub 2 squared minus B Q sub 1 Q sub 2. Cournot defined an equilibrium as a pair Q bar sub 1 comma Q bar sub 2 that satisfies the following 2 inequalities. Pi sub 1 of Q bar sub 1 comma Q bar sub 2 is greater than or equal to pi sub 1 of q sub 1 comma q bar sub 2 for every q sub 1 greater than 0. That is a clove. Pi sub 2 of q bar sub 1 comma q bar sub 2 is greater than or equal to pi sub 2 of q bar sub 1 comma q sub 2 for every q sub 2 greater than 0, which is a diamond. Of course, this is the same as saying that q bar sub 1 comma q bar sub 2 is a Nash equilibrium of the game where the players are the two firms. The strategy sets are capital S sub 1 equals capital S sub 2 equals open bracket 0 comma infinity close parentheses, and the payoff functions are the profit functions. How do we find a Nash equilibrium? First of all, note that the profit functions are differentiable. Secondly, note that Clove says that having fixed the value of q sub 2 at q bar sub 2, the function pi sub 1 of q sub 1 comma q bar sub 2 minus viewed as function of q sub 1 alone minus, I believe those are hyphens, is maximized at the point q sub 1 equals q bar sub 1. A necessary condition for this, if q bar sub 1 is greater than 0, that the derivative of this function be 0 at the point q sub 1 equals q bar sub 1. That is, it must be that the partial derivative of pi sub 1 with respect to q sub 1 of q bar sub 1 comma q bar sub 2 is equal to 0. This condition is also sufficient since the second derivative of this function is always negative. The partial second derivative of pi sub 1 with respect to q squared sub 1 of q sub 1 comma q sub 2 is equal to negative 2b for every ordered pair q sub 1 q sub 2. Similarly, by diamond, it must be that the partial derivative of pi sub 2 with respect to q sub 2 is of q bar sub 1 comma q bar sub 2 equals 0. Thus, the Nash equilibrium is found by solving the system of two equations. The partial derivative of pi sub 1 with respect to q sub 1 of q sub 1 comma q sub 2 equals a minus c minus 2b q sub 1 minus minus b q sub 2 equals 0. The partial derivative of pi sub 2 with respect to q sub 2 of q sub 1 comma q sub 2 equals a minus c minus 2b q2 minus, that is, minus 2b q sub 2 minus b q sub 1 equals 0. Restating that line, the partial derivative of pi sub 2 with respect to q sub 2 of q sub 1 comma q sub 2 equals a minus c minus 2b q sub 2 minus b q sub 1 equals 0. The solution for Q bar sub 1 equals Q bar sub 2 equals A minus C over 3B. The corresponding price is capital P bar equals A minus B of 2 multiplied by the ratio A minus C over 3B, which equals A plus 2C over 3, and the corresponding profits are pi sub 1 of the ratio A minus C over 3B, comma, A minus C over 3B equals pi sub 2 of the ratio A minus C over 3B, comma, the ratio A minus C over 3B equals, open parentheses, A minus C, close parentheses, squared over 9B. For example, if A equals 25, B equals 2, C equals 1, then the Nash equilibrium is given by 4, 4 with corresponding profits of 32 for each firm. The analysis can easily be extended to the case of more than 2 firms. The reader who is interested in further exploring the topic of competition among firms can consult any textbook on industrial organization. Test your understanding of the concepts introduced in this section by going through the exercises in section 2.9.7 at the end of this chapter.